Hello and welcome back. Yes, your eyes do not deceive you. I am indeed in my shark onesie today, bringing you lecture number 2, titled Periods of Motion. So, the first thing that we're actually going to do today is a little bit of a lab. That's right. It's a green bin day. And if you've been to class at all, you know that green bins in the back of the room means we have a lab. So, unfortunately, you don't have green bins at home. But you'll actually see a way that you can participate in the lab with me. So let's go to the lab real quick. All right, welcome to the lab, aka the living room. You may not have a green bin at home, but actually you can follow along with the first part of the experiment using a phone and a phone charger. So if you'd like to participate and follow along with it, grab your phone and your phone charger. Obviously difficult if you're using your phone to watch this. So if you haven't noticed already on the chart on the note sheet, what we're going to be doing in this little lab demonstration is seeing the factors that affect our two different types of simple harmonic motion. So we'll start with the pendulum, which is the part you can use your phone with. So if you're looking at the chart, you see that we're testing two factors for the pendulum. We've got the length of the string and then the mass on the end of the pendulum. So length on the string is length of the string is on the first on the list, so we're going to do that one first. So I've got my little 100-gram mass here, and I'm going to attach it to the bottom. So if you're following along with your charger, you can, Mr. Foster is not liable for any damages that may be happening to your phone or your phone charger by participating in this experiment, but it should be okay. For safety's sake, maybe do this over a soft surface. So if you're following along with home, take your phone charger, plug in your phone here, and you're just going to be pinching it at one point, and we're going to be releasing it and watching it oscillate. So check this out. What we're going to do is I'm going to pull it back and let it go, and we're going to count 5 oscillations to see how fast it's moving. Remember, period is the amount of time per oscillation. So we'll see how adjusting these affects the period of the motion. I'll count to 5 oscillations, and you can do the same with your phone. 1, 2, 3, 4, 5. All right. So that was the amount of time it took for 5 oscillations to happen. Now what we're going to do is we're going to change the length of the string. I've got another loop up here. So we're shortening the length of the string. If you've got your phone and you had it pinched at like this length, then just pinch a little shorter and then start from here and see how that's different. So let's see. Pull it back, count to 5. 1, 2, 3, 4, 5. All right. So that's pretty clear that those periods were a lot shorter, right? It was moving faster. The period was shorter. So I shortened the length of the string, and the period got shorter. So if you're following along with the chart, it looks like the length of the string should go in the does affect period column. Does affect period, because it changed when we changed the length. So let's go back down to the full length, because we're now going to test how mass affects the period. So I've got the 100-gram mass here again, and we're going to go back down to the bottom. So I'll count this one out again just so we get a feel for it before we change the mass. So I'll pull it back. This one, actually, if you're following along with your phone, I'd suggest flipping over to the charger side, because I'm going to be increasing the mass, and obviously the charger side is lighter than your phone. So we'll use this as a lighter mass and just pinch this one and follow along with me by releasing them. All right, so the smaller mass here. 1, 2, 3, 4, 5. All right, so that was the 100 grams. I'm going to bump it up to 500 grams, and we're going to see if that changes the period. So if you're following along with your phone, take about the same length of cord that you had for your charger. Say you had it about at like this length. We're going to use, I attached it at the bottom again, so we're actually using the same length of cord. So take the phone end now, measure out about the same length of cord, and test again using your heavier end, aka your phone, over the charger end. So I'll pull it back and we'll count. 1, 2, 3, 4, 5. So So that didn't seem to change to me. That seemed about the same as our 100 gram option. So it turns out that mass actually does not affect the period of the pendulum. So put that one in the does not affect side of the box, because it was the same. It was the same as when we had the 100. The 500 and the 100 were the same. All right, so that one's all for the pendulum. The next one you see in the box below the pendulum one is the spring example that we saw in the previous video. So these are sometimes called mass spring oscillators because it's mass spring and it's oscillating. But I've got it abbreviated, it's shortened as just spring oscillator, means the same thing. And that's how you see it on questions or other resources. So we've got our spring oscillator, and we've got 3 factors this time actually. So there's the distance that I pull down on it, there's the mass on the end of the spring, and actually also the spring stiffness is what we're going to be looking at. So we'll start with the distance that I pull the mass down, and we're going to I'm going to use the 100 gram again. Unfortunately, unless you have a spring laying around, you can't participate with this one. You'll just have to follow along with me. So first one, we're going to test distance that the spring is stretched. So I'll pull it down about here, release it, and we'll count to 5. 1, 2, 3, 4, 5. All right. So now I'm going to stretch it further. So what you might be thinking, if you're predicting along with this, is if it's got further to go, that the period might be longer, right? Because it's got further to travel. Let's find out. So I had it about here before, right? I'm going to stretch it down out of the frame of the video. We'll see. 1, 2, 3, 4, 5. That was about the same, if I do say so myself. So yeah, it turns out that the distance that you stretch the spring actually does not affect the period. Interesting. So put that one in the does not affect box. So we've heard the 100 gram count twice. So the next one we're going to test is mass on the end of the spring. So I'm going to go from 100 up to 200. Unfortunately, we're not using our friend the 500 gram mass because it's going to break my spring. So unfortunately, this one hangs default a little bit below. Actually, I'm going to move the camera down a little bit so you can see it. There it is. So you can kind of see that. It's really close to the table edge. But let's see how this increase in mass affects the period. 1, 2, 3, 4, 5. So that was much slower, right, than the 100 gram. So it looks like increasing the mass increased the period as well, right? It was longer. It took longer to do one oscillation. Increasing the mass increased the period. So mass does affect the period of the spring oscillator. Make sure that you're putting these ones in the spring oscillator box. Last but not least, we've got the spring stiffness, how that affects it. So I'm going to go back to using our 100 grams here. Actually, we had a feel for the 200. I'll use the 200 again because this one actually doesn't work as well because I don't have another spring, but what I do have is a rubber band. So this spring is really stretchy. It has a pretty low K value, whereas the rubber band is a lot stiffer, even though rubber bands they're not car shocks by any means, but it's a lot stiffer than that spring is. So you heard me counting before. It was 1, 2, 3, right? It was taking a very long time for the spring to pull up on the mass. Unfortunately, since the rubber band is so stiff, this isn't going to work very well. But I just want you to pay attention to how fast the mass is actually bouncing up and down. If it falls, it falls. So it doesn't move very much. See, it fell. It doesn't move all that much, but you saw it go bum bum bum. Like it moves. It's bouncing up and down pretty fast. So it was hard to measure, but actually. It should be clear-ish, at least, that increasing the K value actually increased or decreased the period, right? It was moving faster, so it was taking a shorter time per oscillation. So it looks like increasing the K value does change the period. It does affect the period. K value goes up, period goes down. All right, the chart's complete. Now let's move on with the rest of the lecture. Welcome back. I hope you enjoyed our visit to the lab. I hope to return there often because I think it's a nice way to keep up the demonstrations and the visualizations going, despite the fact that we're over the internet. But so let's continue with the rest of our notes sheet here. So we actually have one definition to talk about before we can continue talking about the factors that affect the period of a motion. And it's right there, it's restoring force. So what the restoring force is a force which pushes a system back to its rest position. Write down the definition. It might sound a little bit confusing at first, but I'll help by drawing a little bit of a picture. So you've got this diagram here on your note sheet where we've got two panels with a pendulum and two panels that have the spring oscillator, this time horizontal spring oscillators. So let's take a look at the pendulum one. So I'm going to draw out the little pendulums here, one on the left and one on the right. So the pendulum's rest position is right there, straight up and down, right? That's where it would be at rest. So a dotted line here down the middle of each of these to show what the rest position is at. So my question is, what is the force that is pulling that pendulum back to that rest position? What's the force that's pulling it down into the middle there? This is my best Dora the Explorer. Right. Yeah, so if you said gravity, you're right? Let's take a look. So gravity is pulling down here on the pendulums, right? Each of it's pulling down. And the gravity is what's causing it to be pulled back, right? There's a component in this direction that's causing it to be pulled back down towards the middle, right? Gravity's pulling it and swinging it in. So the gravity here is the restoring force for the pendulum. I'm going to erase this, and we'll go to the spring oscillator. So for the spring, I'll draw my two little horizontal springs here. What you notice, there's this dotted line right here on each of these that says on your sheet, it says spring or unstretched spring length rather. So at that unstretched spring length, right, it's where the spring wouldn't be pushing or pulling. The spring is at rest, right? I've got my bin here. So when the spring is at rest position, it's sitting still, it's not pulling on anything, right? But when you are, let's look at the panel on the left, where the box is inside, it's to the left of on your sheet, right? So it's inside of the unstretched spring length, so the spring is compressed, right? And if you compress a spring, it's trying to push out, right? So on this little drawing, the spring is trying to push the block to the right, and on the other panel, this is the force of the spring. I didn't label it. On the other panel, the spring is stretched. So when the spring is stretched, which way is it trying to pull the block? Right to the left, right? It wants to go in this way. Force of the spring, right there. It's pulling it to the left. So in this case, what's the restoring force? It's the spring, right? The force of the spring. That's the restoring force. Lovely. So we're going to utilize these ideas of the restoring force when we look at the problems that we've got. So there's two formulas, one for each of these. The formulas, fair warning, are a little bit ugly, but now that we've done the demonstration and talked about restoring force, they might make a little bit more sense. So the first one that's coming up is the period of a pendulum. Now, period, remember, is right here, a capital T. And we'll be specific, right? Period of the pendulum, TP. So for the period of a pendulum, this is the formula. It's 2 pi, gross, times the square root, u, of the length of the string, represented by the script L, divided by acceleration due to gravity, g. So that's how we calculate the period of a pendulum. Now, again, that looks kind of ugly. There's a whole crazy proof behind it too, but I don't think you want me to go through that. You guys would get very uninterested very fast, I think. So let's look at what this is saying. So we did an experiment just now to calculate and determine the period of a pendulum. So let's look back and see what factors affected it. If you flip over to your chart, you see that the only thing that we measured that affected it was the length of the string. So let's look at L. L says L's on the top of this denominator here, or this fraction here rather, it's in the numerator. So when L gets larger, the period gets larger. And that's backed up by our experiment, right? When the string length was longer, the period was longer as well. It took longer to swing back and forth. So our experiment backs that up. It backs up the math. Now, the G. Unfortunately, I can't change acceleration due to gravity on Earth to show you that it would affect it. But think back to the restoring force. So the restoring force, we said, in a pendulum was the force of gravity. And it turns out the restoring force has an effect on the period. So let's see. In the formula, it says that if G goes up, right, if G gets bigger, then period will get smaller, right, because G is on the bottom of the denominator. The bigger the denominator is, the smaller our number gets. So if we went to the moon, where there's less gravity, the period, the G would go down, right, which means that the period would increase. It would move slower. This kind of makes sense. If gravity is pulling it down harder, it's pulling it down to the center more, then it'd be swinging back and forth faster. So that kind of makes sense. Now, let's take a look at the problems. I'll erase this formula. Actually, no, I'll leave the formula at the top so that we can reference it. Number 1 says a pendulum oscillates 30 times over the course of 6 seconds. If this experiment takes place on the surface of the Earth, meaning that gravity is G, 9.8, right? What is the length of the string? So we're given oscillations. We have a number of oscillations of 30. And we have over the course of 6 seconds. So our time, delta t, is 6 seconds. What we're looking for, well, actually, hold on. It says the experiment takes place on the surface of the Earth. So on Earth, right, we have acceleration due to gravity g of 9.8 meters per second squared. Positive 9.8. Remember, g, gravity, is positive. A, acceleration due to gravity, is positive or negative depending on the direction. So g is positive 9.8, just because of the way we define it. So the question it's asking us is for length of the string. L, script L, question mark. So we have number of oscillations and delta t. We know from the previous lesson, lesson 1, that we can use these to calculate period. So period, t, period, we're looking at a pendulum, so I'm actually going to be more specific and write TP, toilet paper, I hope you're not out, is equal to delta t divided by number of oscillations. Right, the time per oscillation. So our time is 6 seconds. And our number of oscillations is 30. So we get a period of 1/5 seconds, right? Seconds divided by nothing. Seconds divided by 1, rather, is seconds. So 1/5 of a second is what our period is. Our next goal is length of the string, right? Well, what if we use that handy-dandy formula that relates period to length of the string? So I'll rewrite the formula out. TP, the period of a pendulum, is equal to the square root of length string divided by gravity. So we plug in what we have, right? We have 1/5 as our period of the pendulum, right? 1/5 of a second is equal to 2 pi times the square root of L, which is the length of the string, which we don't have, right? We're looking for that, divided by G, which we're on Earth, so it's 9.8 meters per second squared. All right. Hope you've got a calculator handy for this one if you're trying to do it on your own. You're solving for L here, so we'd need to square it, or we'd need to divide by 2 pi, square it, multiply by 9.8. Yay, insolve, right? L, the length of the string, is equal to, or string, is 9.9 times 10 to the negative 3rd meters, which looks kind of ugly, but that converts to 0.99 centimeters, so basically 1 centimeter, which is pretty darn short, right? If you remember our swinging back and forth experiment, I was counting those out, 1, 2, and those were pretty those were a lot longer periods, and we learned that shortening the length of the string made it go faster. So 1 centimeter is a really short string, and it was oscillating 1 time, or it was oscillating 5 times a second. So that's pretty darn fast. So that checks out. That makes sense. 0.99 centimeters. Great. On to number 2. Number 2 is basically the same setup as number 1. So if you would pause the video real quick, find you some paper, and try out number 2 on your own. Pause and try it. Did you try it? Okay. So number 2. Number 2 says a pendulum oscillates with a string length of 0.75 meters. So our L, string length, is 0.75 meters. It asks what is the period of the pendulum's motion. So we're looking for the pendulum of a period. We don't know that, question mark. What you might notice here, that a piece of information that we got in number 1 that wasn't in number 2 is that we're on the surface of the Earth. Now, if it doesn't, the problem doesn't say that we're on the surface of the Earth. Usually we're on the surface of the Earth, right? We do our problems on the Earth. So G is 9.8. So G here is also 9.8 because it's assumed that we're on Earth doing this experiment. Great. So we're looking for period. We have a length, and we know G because we're on Earth. We can just use the formula, right? Period of the pendulum is equal to 2 pi square root of L over G. 2 pi, just plug in. L is 0.75 meters. G is 9.8 meters per second squared. So our period of the pendulum is 1.74 seconds. Lovely. Hope you got it right. Good job if you did. That brings us to number 3. Number 3, again, we're just using the same formula. So if you'd like to try that one on your own, also go ahead, pause it, and try out number 3. I'll erase in the meantime. Lovely. Number 3. Unless you want to pause it and go. No? Yes? Number 3. So number 3 says the pendulum's length is extended to 1 meter. And then it asks how many oscillations does it make. So extended to 1 meter. Let's take a look at what that is. This is related to sort of set in the same problem 2, but we don't really use anything from problem 2. So number 3, our length is 1 meter. It says if it's set to oscillate for 15 seconds, so 15 seconds is our time, delta t equals 15 seconds, how many oscillations does it make? So we're looking for number of oscillations. We don't know it. Again, implied variable here, a variable that it gives you is that we're on the surface of the Earth. So we do know G. G is equal to 9.8 meters per second squared. And with that, we actually have all that we need to solve. So we're given length and we have G. So just like in number 2, we can use those things to calculate period. So go ahead, let's do that. Period of the pendulum is equal to 2 pi times the square root of L over G. Just to rewrite the formula, 2 pi times the square root of, in this case, our length is 1 meter, and G is 9.8 meters per second squared. All right, so I forgot to calculate this one. So hold please while we phone calculate. Square root times 2 times pi. Is there a pi on the phone calculator? There it is. So what I got is the period is 3 equals 2. A period of 2.01 to be very, very specific seconds. Great, so we have period now. But that's not the answer to the problem, right? The problem's asking us for number of oscillations, so it's just one more step, basically like the stuff that we did yesterday, or in the previous lesson. I keep saying yesterday. So the period is equal to delta t, right? Time per oscillation, delta t, divided by number of oscillations. Our period is 2.01, and it's okay if you use 2, that's fine. Our time it gave us was 15 seconds, divided by number of oscillations, which is what we're looking for. 15 divided by 2.01 is equal to 7.46 oscillations. Lovely. So those are our problems for period of a pendulum. It's pretty much all it is, right? You just use the one formula, have what you have, don't have what you don't have, and then solve for what you need. Great. Let's move on to our next set of problems, which are the period for a spring oscillator. This video is already looking a little longer than the last one, right? But that's okay. At least it's not an hour long in class, right? So, period of a spring oscillator. Looking back at the chart, we saw that things that did affect the spring, right, was mass, and we sort of saw that the spring constant K affects it. So here's the formula. We have Ts this time, right? The period of a spring oscillator is, it's going to look familiar, 2 pi times the square root. But this time we have mass and the spring constant, right? So we have mass divided by K, the spring constant, the stiffness of the spring. So let's see if this backs up our experiment. So what we saw in the experiment is if we increased the mass, it was bouncing slower up and down, right? So period went up. Increased mass, increased period. That checks out with our formula. And we changed the spring constant, right? We moved to the stiffer rubber band, and the rubber band was bouncing the spring faster, right? So the period was faster, and we can see the period, it was faster, so the period was smaller. We can see that if K goes up, if we get stiffer, the spring gets stiffer, K goes up, period should go down, meaning it's bouncing faster. So the period, or the formula checks out with our experiment that we did. Lovely. All right, we've got a couple of problems for this one, which look very similar to the period, or the problems that we did for the pendulum's period. So let's take a look at number 4, aka our first one for the spring. Number 4 says, a spring with a spring constant of 25 newtons per meter is set into SHM, meaning simple harmonic motion, oscillation, with a 1 kilogram mass on the end of the spring. What is the period of the oscillator's motion? So it says spring constant of 25 newtons per meter, that's K, 25 newtons per meter, is set into oscillation with a 1 kilogram mass. So our mass on the end is 1 kilogram. Make sure that any masses that you see, the mass here that it's asking about is the mass on the end of the spring, right? Because that's what we changed. So 1 kilogram mass on the end. And it's asking us for the period of the spring, Ts, question mark, right? Period of the spring, that's what we're looking for. Just use that formula, right? Pretty straightforward. We have M, we have K. We can use our formula to solve for a period. Period is equal to 2 pi square root M over K. Just plug in what we got. 2 pi, our mass is 1 kilogram. The K value is 25 newtons per meter. And 1 kilogram divided by 25, square root 2 pi. This one's just math, right? And solving here. I got the period is equal to 1.26 seconds. Great. All right. Much like the previous problems, the other two are just kind of extensions of the same one. So go ahead, and even you could just try 5 and 6 right now before we move on. Or you can do 5 and then 6 and wait. Whatever. The world is your oyster. I'll erase, and you can decide. Okay. So, number 5. Pause if you want to do it before I do. So, number 5 says, if the period of the motion of a spring oscillator system is 1.25, and the mass on the end of the spring is 3 kilograms, what is the spring constant of the spring in the system? All right, so the problem says period of our system, which is a spring, is 1.25 seconds, and the mass on the end of the spring is 3 kilograms. So our mass on the end is 3 kilograms. And the question is, what is the spring constant of the spring in the system? We're just looking for spring constant, which is K. Once again, we have enough information just to plug into our period problem. So write it out, variable form. Spring constant is equal to 2 pi, or sorry, period is equal to 2 pi times the square root of mass divided by spring constant. Our period was 1.25, 2 pi, square root, 3 kilograms divided by K, because we don't know K, that's what we're looking for, right? Now we have to do a little bit of mathy solving stuff. If you do that mathy solving stuff, you should get K is equal to 75.8 newtons per meter. Newtons per meter. If you find yourself having issues with the algebra stuff, message me and I can break it down for you, and I'll link that video in Google Classroom or something. So be sure to message me if you're having those problems. Okay, on to number 6. Last but not least, number 6 says the spring in the previous problem is replaced with one that has double the spring constant of the one in problem 5. Oh, sorry, we have 2 more. This isn't last but not least. If the mass on the oscillator does not change, what is the period of the new oscillator? So we've got a new spring constant that's twice the one from the previous problem. So in the previous problem, we had 75.8 as our K value. So in this case, if we double that, our K value is 151.6 newtons per meter. And it says the mass does not change. So our mass is still that same 3 kilograms from the previous problem. And we're asked about the new period. Our new period is what we're looking for, question mark. All right, we have M, we have K, we can solve for period. Period is equal to 2 pi times the square root of mass divided by the K value. So 2 pi, just plug it in here, times the square root of 3 kilograms divided by 151.6 newtons per meter. So if you do that math there, again, this one's just straightforward, no solving, you should get that the period is equal to 0.88 seconds. 0.88 seconds. So if you noticed already, we've increased the K value here, so it makes sense for the period to go down. That backs up our experiment and our understanding of the formula. So that makes sense. We doubled the K value and the period went down. That checks out. So now that I've started using that language with doubling the K value and seeing how that affects, that might lead you to predict what our next couple of problems are going to be like, which are indeed some relationship problems. So 7 and 8 here are 2 relationship problems. The first one, number 7, says a pendulum oscillates on a string. If the length of the string is increased to 9 times its length, what effect does this have on the period of the pendulum's motion? So we're looking at pendulum motion here, and we're doing a relationship problem, right? You see that we're looking at how something changes and affects something else. Relationship problem. So remember, in a relationship problem, we always start with the formula. So we're looking at period of a pendulum. The period of a pendulum, TP, is equal to 2 pi times the square root of L over G. So remember, we always ignore constants in our thing. So 2 pi goes away. Now let's look at the problem. It says the length of the string is increased to 9 times its length. So remember, in the relationship problems, we're looking at how values compare to their original value. So it's 9 times larger, meaning we plug in a 9 for the L, right? looking at how many times larger it is from its original, or how many times it's changed from its original value. So it's 9 times larger, so we plug in a 9. And it does not say anything about G. So assumedly we're on the same planet, meaning G stays the same, right? And remember, if something stays the same, we plug in a 1 over 1. So we've got the square root of 9 over 1. That's just 9, right? Square root of 9 is 3. So it turns out if we multiply the length of the string by 9, we increase the period by 3. So it's got a quadratic relationship, right? We've got the square root there, meaning that we have to take a square root in order to relate the problems. So this checks out, right? We got the square root, 9 times larger, only 3 times larger for the period. Lovely. Just a relationship problem, not scary. So that brings us to number 8. Again, it's just a relationship problem, but this time it's with a spring. So feel free to try that one out on your own. But I'm going to do it now because you can pause it if you want to. So number 8 says, in a given spring oscillator system, the mass is increased by 4 times. What effect does this have on the period of the oscillator's motion? So this time it's a spring oscillator, and we're increasing the mass. Remember, when we increased the mass before, what happened to the period? It went up, right? It was moving slower, so it went up. So we should expect, if we're increasing the mass, that we should increase the period. But let's find out. Relationship problem, so we start with the formula. The period of the spring is equal to 2 pi square root m over k, mass divided by spring constant. We ignore the constants, right, because those aren't changing in a relationship problem. So let's look at mass. Mass is increased by 4 times, so we plug in a 4 for mass. And the spring does not say anything about it, so it does not change, right? We're using the same spring, basically, just changing out the mass on the end of the spring. So k doesn't change, so it gets a 1. 4 divided by 1 is 4. Square root of 4 is 2. So the period of the spring is 2 times larger. Makes sense, right? It goes up. That's what we predicted, right? So again, the quadratic relationship here because of the square root. So increasing by 4 times, increasing the mass by 4 times rather, means that the period is only increased by 2 times. But it does check out that it goes up, which is what we said. So yeah, 2 times larger. That's all that we have for this. Feel free to watch again if you need to, and fill out that exit ticket on Google Classroom. Remember to hit mark as done, which is on that remind message that I sent out. Be sure to do that, and I'm going to catch you next time.